Mechanical waves. Now the problems are getting a little more interesting, I think. Here we have two different kinds of strings. We have a longer string. I've drawn it in blue and sort of made it look a little thicker and fatter than the black string next to it because it has a higher density. Longer string with a higher density and a smaller string shorter with a lower density. And they're connected, and where they're connected we want to have a node. We're going to drive some type of mechanical wave, wiggle one end of the string so we get a mechanical wave set up, and we want a node at that point where the two strings are connected. So if we just look at the smaller string, the 1 1/4 meter, then we want a wave that's going to look like that, or like that, or like that, right? Either the first, second, or third harmonic here. We don't really care. We don't really know right now. We're going to figure it out. But as long as there's a node at each end, we're happy. And we need that condition for both strings. Okay. So we have the lengths of the strings, and we need to know if that's a multiple of lambda, right? Because it has to be a multiple of the wavelength in order to get a node at both ends. So we need lambda. We need the wavelength. And there's one thing that we know is true for all waves. The speed is the wavelength times the frequency. And these are strings. And there's something we know about strings. We know that the velocity, the speed, is the square root of the tension over the density. So we combine these two, and what do we end up with? We end up with lambda times the frequency is the square root of the tension over the density. And we also know something else here. We know that we want to have an even multiple of lambda to be our length, right? So the condition we're looking for, I'll just write it here, the condition that we have nodes at both ends is this. It's that the lambda is 2L over n, and n can be 1, 2, 3. So for all those wavelengths, we will have standing waves with nodes at both ends. Now the other thing to remember is that n can be different in the two strings. So we've got a smaller string on the right. We've got, that's this 1.25 meter string. We've got the longer string on the left. And they can have different numbers of nodes. The ends can be different. But what has to be the same in both? The speed of the wave is going to be different because they have different densities. The end could be different. But the thing that has to be the same in both is the frequency. We're driving the whole system at one frequency, and that has to be the same for both strings. So I'm just going to combine these last two equations here, and I'm going to get the frequency of the nth harmonic is going to be n over 2L, the square root of the tension over the density. So that's my equation that I need. Now what I'll do is I'll go in and I'll find, the first few frequencies for each, and I'll see where do I get a common frequency. So let me move on down here, and I'm going to have my my N value. I'll make a little table, and my 3.75 meter string, and my 1.25 meter string. And so the first thing I care about is the fundamental, right, when n is 1. And so f sub 1 is going to equal 1 over 2 times 3.75 times the square root of 190 over 6 times 10 to the negative 2. And what I get is 7.5 hertz. And I'll do the same thing for the other string. And n is 1, 2 times the length, 1.25 meters. The tension is given. Tension is the same in both strings. They're connected together. And the density is a little less, right? 1.5 times 10 to the minus 2. And I've got 45 hertz, 45.02 hertz. So that's a lot bigger than my frequency for the 3.75 meter string. So I'm going to keep going up for 3.75 and see if I get one that equals 45. And if I jump over 45, then I'll keep going and I'll look to see what the next one up is. The next one up is going to be twice as big, right? F sub 2 here is going to be twice as much as this one, 90.04 hertz. But let's see where we end up with. So I'm going to keep going over here. So this is going to be n is equal to 2. And that's going to give me 2 over 2 times the length. And I've got the square root of the tension over 0.06. And that is 15, right? Twice as much as the previous one. And I'm going to put for n equals 3. I'm not going to punch in all the numbers this time. And n is equal to 4. And for 5, and let's see, I think this is going to do it. All right, so when n is equal to 6, I've got a frequency of 45 hertz. And that gives me six loops, right, on the left-hand side in the longer string, and that matches up to the frequency that gives me 1 loop in the right-hand string. So let me draw a picture of what this thing looks like. In fact, I'm going to pause and do it, and then we'll come back. Okay, I think I've got it here. This line marks where the two strings are connected, the node. We wanted that node at that point there. The short string on the right hand side has n is equal to 1. So one loop there of the string, which is half of a wavelength, right? The length is equal to half of the wavelength. And on the other side, we have 6 of those loops going, which is 3 lambda. The length is equal to 3 lambda. So here n is equal to 6, here n is equal to 1, and that gives us a node at the point where the two strings are connected with the same frequency driving the whole system, 45 0.02 hertz.